In this video, I will be explaining how to plot a Bode plot for a high-pass filter. Given the transfer function above, we are asked to plot the magnitude and phase. First, we would have to simplify the transfer function and put the equation into standard form. As mentioned in class, the standard form for any zero pole would be s over z or s over p plus 1. So if we look at the 0 s plus 10, you get a 0 in standard form of s over 10 plus 1. With a constant of 10. This would be repeated for each zero and pole. Once this is done, you'd get the following transfer function. However, as you can see, some of the constants still need to be simplified. Once all the constants have been simplified, this is the transfer function you would get. However, to write out the actual magnitude and phase equations, we want to rewrite this S-domain transfer function into omega domain. To do this, you would just replace the s with j omega. This is the rewritten transfer function in omega domain. So, the terms at the top are the zeros, and the terms at the bottom are the poles. The constant in green is the constant k. To determine the magnitude equation, we would take the 20 log of each of the terms, including the constant k. So, you would take the 20 log of 4 over 25, and you would take the 20 log of each of the zeros and poles. However, you'd have to take care of the sign. The 20 log of a 0 would have a positive sign in front of the 20 log. However, for a pole, you'd have a negative sign in front of the 20 log. Taking into account all of this, you'd get the following magnitude equation. At the front is the constant. These three are the zeros, and these two are the poles. As you can see, they both have negative signs in front of the 20 log. Using this equation, we can then plot each of the zeros, poles, and the constant. The zeros would increase at 20 decibels per decade at the z value, and the poles would decrease at 20 decibels per decade at the p value, while the constant, 20 log 4 over 25, would be at a constant of around negative 15. By combining all of these lines, we can then plot the magnitude. This would be the final magnitude plot. Using this plot, we can then determine the filter. As mentioned above, it is a high-pass filter, and we can confirm this using the plot. Be sure to take note of all of these frequencies, as this is where the changes, such as the zeros or poles, occur. The graph starts at negative 15 because of the constant. Let's move on to the phase equation. Using the transfer function in the omega domain, we can write the phase equation by determining the angle of each term. The constant would have an angle of 0 degrees, and you would take the inverse tangent of the zeros and poles. However, similar to the magnitude equation, you would have to take care of the sign in front of the inverse tangent. For the zeros, the sign would be positive, and for the poles, the sign would be negative. Taking this into account, you would get the following phase equation. As you can see, the constant has an angle of 0 degrees. These would be the zeros, and these two would be the poles. Using this equation, we can graph each of the zeros, poles, and the constant. And you would get the following graph. The zeros would have a slope of positive 45 degrees per decade between z over 10 and 10z, while the pole would have a slope of negative 45 degrees per decade between p over 10 and 10p. Combining all of these lines, we can finalize the phase plot. This is the final phase plot. Be sure to take into account all of the frequency points, as this is where the changes such as the zeros and poles occur. This is how you would plot the Bode diagrams of a high-pass filter. Thank you for watching, and I hope this was helpful in understanding how to plot a magnitude and phase plot of a given transfer function. Thank you.
Hello everyone, my name is Michael Singh, and today I will be discussing with you how to plot an all-pass filter in Bode paper. Okay, so the first thing we're going to do is we're going to rewrite our h of s transfer function equation in terms of h of omega. So we're just going to replace the s's that we see with the j omegas. That's going to be the first step, pretty simple. Then for step 2, we're going to go ahead and factor out the appropriate terms such that we leave our equation in terms of j omega plus 1. So in this case, we factor out a 40 in the numerator, a 10 in the denominator, and we're left with 1 plus 2j omega and 1 plus 5j omega respectively. And what we need to take note of, this is very crucial, is that you can't have a number being multiplied to the j omega. You can only have a number being in the denominator, or the j omega being divided by a number. So what we do is, in the case of the 2j omega, and you can do this with any number, is we go ahead and we rewrite it such that it's in the denominator. So 2j omega becomes j omega over 1/2 or j omega over 0.5. So that's going to be step 3, where we rewrite our equation in that form. And we'll be left with this general h of omega equation, where we have h of omega is equal to 20 log of 4, which is our new constant, 20 log plus 20 log of 1 plus j omega over 0.5 minus 20 log of 1 plus j omega over 0.2. And this is going to give us a constant of 12.04 in the magnitude plot and a 0 constant for the phase plot. And the 20 log 1 plus j omega divided by 0.5 is going to give us a 20 decibel per decade positive slope happening at 0.5 in the magnitude plot, and a plus 45 degrees per decade slope in the phase plot. And then the negative 20 log of 1 plus j omega over 0.2 is going to give us a negative 20 decibel per decade slope happening at 0.2, and a negative 45 degrees per decade slope happening in the phase plot. So we'll go down here and start plotting. And so we'll start with the magnitude plot, and as you can see here, our constant starts at negative 12 or a positive 12, and it stays flat throughout the entirety of the plot. And our pole starts at 0, and it goes all the way down to 0.2, and at 0.2 it starts to go down at negative 20 decibels per decade. Similarly, our 0 starts at 0, and it moves all the way down to 0.5, and then it starts going at 20 decibels per decade. So our final plot, which is the highlight in yellow, it starts at 12.04, stays flat, then it gets to 0.2 radians per second. It heads down at negative 20 decibels per decade. It gets to 0.5, and those two slopes cancel out. And so we're left with a flat line that never goes under the x-axis. That's very important. And for our phase plot, we get everything starting at 0, and then we get to 0.002 rather for our pole, and it goes down at negative 45 degrees per decade all the way till 2. And for the 0, it starts at 0.005, and it goes all the way to 5 at 45 degrees per decade positive slope. So our final answer starts at 0 until 0.002, then it heads down slightly at negative 45 degrees per decade, and we get to 0.005, and that slope of positive 45 cancels the negative slope of negative 45, and we stay flat until we get to 2, and then our 45 slope remains, the positive one. So we go back to the 0 line, and we stay flat there for the rest of the graph. And so the key thing to take note of here is that while it looks like we maybe have a low pass filter in our magnitude plot, the plot never went below the x-axis. So really everything passes. That's why we call it an all pass filter. So you want to take note of this. If the plot never goes below the x-axis, everything passes, all signals go through, and we have what we call an all pass filter. I hope that helps, and good luck.